Right, so the first part of the talk was more about the materials side and the effects that you can get out of them. Now I want to start to focus on planar waveguide systems, what you can make them out of, what you can do with them. So, in order to make a chip-scale processing device, there's a number of things that you actually need to get from the material. First of all, it has to have low loss. It also has to have high nonlinearity and a good figure of merit. In order to get low switching powers, which are desirable in things like telecom applications where we don't want to be plugging kilowatt lasers into them, we actually want to have a material that's got a high refractive index in order that we can make devices with small mode areas and hence get very high intensities with low powers. Obviously, you've got to have a way of being able to make low-loss waveguides in a system. And in an ideal world, we'd also like to have a high damage threshold, because when you start to squeeze some of these mode areas right down into the sub-square micron regime, you can very rapidly get to gigawatt per centimetre intensities. So the solution that we've been pursuing is based on chalcogenide and telluride glasses, which I'm guessing many of you have probably never heard much about. So I'll spend a few minutes talking about what these materials actually are. So in the first instance, chalcogenides are actually amorphous semiconducting glasses that are made up of various materials, but one of the large constituents is one of the chalcogen elements, which is sulfur, selenium, and tellurium. Typically you use glass formers such as arsenic, germanium, even silicon, and other network modifiers, maybe like antimony as well. Chalcogenide glasses are usually grouped by the chalcogen element that you actually got in them, and there's a reason for that. Because when you look at the transmission of the glass, this is what you see. Now, sulfide containing glasses cut off somewhere around the 10 micron region. Selenides go a bit further out to about 15, and tellurides go out to somewhere in the 20 micron region. And this is basically a result of the mass of the sulfur, selenium, or tellurium atoms. Because this is the multi-phonon edge. The heavier the thing is, the lower the vibration frequency, the further out this way you can go. But what's important about this is that we've got coverage here from more or less the edge of the visible right out into the mid-infrared. There are a number of commercial chalcogenide glasses available today. The ones that are commonly available are arsenic trisulfide, arsenic triselenide. There are a number of germanium arsenic selenium glasses with trade names like AMTIR1, which stands for amorphous material transmitting infrared. Gassier, I can't remember what Gassier stands for, but it stands for something. Two flavours of that. So-called GST, germanium antimony tellurium. That is very widely used. In fact, in recordable DVDs, and very shortly in the upcoming replacement for hard disk drives, which is called phase change memory, and so-called TESS, tellurium arsenic selenium glass, which is one of those very long-wave infrared glasses. And typically today, the reason these glasses are available is they have uses in recordable devices, phase change memory, and also lenses for thermal infrared imaging cameras. Tellurides, on the other hand, are basically tellurium dioxide-based glasses, which means they have quite different characteristics to chalcogenides. They are, however, the most non-linear oxide glass discovered to date. And in comparison with chalcogenides, they have a somewhat shorter wavelength multi-phonon edge, typically out to maybe 7 microns in some cases. But the upside is that the band gap is down towards the UV, which means you can also do things with them in the visible that you can't do with chalcogenides. So these materials have quite a lot of interesting properties, and I'm just going to touch on some of those now. First of all, they have both high linear and non-linear indices, and low linear and non-linear absorptions, which we've seen is actually quite important. Because they're glasses, because it's an electronic process, they have ultra-fast response times as well. Talking about the size of their non-linearities, this is the plot that you saw earlier that shows basically the linear index against the chi3. The tellurides sit somewhere here with about 30 to 100 times the non-linearity of silica, and the chalcogenides sit up here with 100 to 500 times the non-linearity of silica. So those are quite large numbers. Importantly, these materials, because they're made up of just a mix of different elements, have quite large glass forming ranges, and hence you can actually tune the composition and tune the behaviour of the material. That's important if you want to make, for example, buried channel waveguides where you need a core and a cladding material. They're also photosensitive materials, which means that you can build a device, say like a Mach Zehnder interferometer. You can then balance it up by irradiating one of the arms to induce an index change. And the other big thing that photosensitivity is important for is to make Bragg grating filters. Here's an example of a waveguide grating in an arsenic trisulfide waveguide. You can see that this is pretty much 35 dB deep. This is limited by the measurement method, not by the grating. So you can make quite strong gratings in these materials. As we talked about just in the first part of the presentation, you can do polling of these materials as well to get potentially large second-order effects and electro-optic effects. Still a lot of work to do on that to really get there, but it's going to happen, I believe. Interestingly, tellurites and chalcogenides are also strongly acousto-optic, and in their respective transmission windows have extended material for acousto-optic cells. So that allows you to build things like very wide bandwidth tunable filters. Again, there's work to be done to exploit that in a guided wave implementation, but it's another opportunity. They're also excellent hosts for rare earth-based ion amplifiers. And to give some insight into that, this somewhat messy picture is a compilation of some of the emissions in tellurites and chalcogenides, spanning basically from 500 nanometers out to 8 microns. And these are the only holes in that spectrum that don't have some kind of emission. It's a long step from emission to an amplifier, but nonetheless that bodes pretty well, particularly when you think how hard it is to generate much beyond this point here in terms of light sources at high power. These materials, curiously enough, also have magneto-optic properties from which one can contemplate building non-reciprocal devices. And chalcogenides, as I said before, are actually semiconducting, so there are some other potential avenues to explore there to see if there are other effects that one can exploit. And most importantly, both classes of materials can actually be deposited and processed with standard semiconductor methods, and we'll talk a bit more about what that means in a minute. Chalcogenides typically have larger effects than tellurites do, but with both material systems, the range of functionalities you've got here gives you an opportunity to consider doing system-on-a-chip type devices in the near-infrared and mid-infrared. What do I mean by that? This would be a kind of example of that. A sort of schematic idea of how one might try to make a range gate spectrum remote sensing device. So what we've got in this schematic here is a tunable mode lock laser here, based on rare earth dope-based waveguide gratings nonlinear switch. Up here we then go down into a nanowire device that will generate supercontinuum. And up here an electro-optic switch so that we can switch the pulse out and then gate by distance what comes back and go into a spectrum analyzer on chip here. So what you're talking about here is being able to send out maybe, say, 3 to 5 micron light and then look in a distance resolved way at the spectrum of what comes back. So you might use this, for example, in an atmospheric system to sense the concentration, say, of carbon dioxide as a function of height in the atmosphere. Would be one sort of thing you might do with this. So these two material systems are actually quite different. What's different about them? First of all, tellurite materials tend to be much more chemically resistant and mechanically stable, which is good for making waveguide devices because they're easier to work with. Tellurite glasses can also be melted in an oxygen atmosphere and survive oxygen-based processing, such as plasma processing, which again is easier to work with. The band gaps of tellurite is typically in the UV, so unlike chalcogenides, they're not photosensitive to normal 1550 type radiation. There's also a suggestion out there that tellurite has a higher damage threshold. And lastly, but not least, this has been a particular bugbear for us in a lot of the chalcogenide work that we do. arsenic trisulfide, it's a supposedly simple two-element binary glass. Well, it's about the most complex binary glass I've ever seen. There are about 7 different phases of it. It does some absolutely bizarre things, even in the melt condition, and that causes a lot of grief. Tellurites are much simpler and easier to work with in that sense, because they have less interesting phenomena. The trade-off is that tellurites also have smaller non-linear effects. Okay, so how do we make waveguides out of these devices? So there's a number of options that one can pursue here. The classic approach is to deposit a thin film and then etch it away to leave yourself with a waveguide. So you deposit with sputter or evaporation methods typically, and etch with either wet chemistry or plasma etching. The usual challenge in this case is the lithography and etching issues, which we'll touch on a little more in a moment. There's also another route one can use where you deposit a thin film, hit it with a high-power femtosecond laser, and photopolymerize the material, and then develop away what hasn't been polymerized. This has been exploited particularly in arsenic trisulfide and a number of other glasses as well, but it is quite specific to the particular glass that you're working with. It does not work with all materials. Another solution that one can consider is to make a strip-loaded waveguide, where we only actually need to make a film of the waveguide material, and then we put a strip of another lower index material on the top to strip load it and make a waveguide. It works very nicely, gets away from a lot of the issues involved in etching the materials. The downside is that it's very hard to get tight bend radii and very small mode areas with that technique. Another commonly used method is liftoff, where we define a mask of some sort that has an overhang, so that when you deposit material into it, you get shadowing and a 2D structure. And then you can get the resist remover in underneath to dissolve off the resist. One downside to that is it requires 2 depositions to make a rib waveguide if you want to do that, and it's very hard to control the sidewall geometry as well. Another method that's been used is laser direct write, and here we're talking about making a film of the material, hitting it with either band gap radiation or femtosecond pulse radiation, 2 completely different mechanisms apply, but you can generate a refractive index change from doing that. Again, works reasonably well. Waveguide losses haven't been great, but there's another fundamental problem. You have a problem with getting high index contrast. And then one method that's been coming into play recently is actually something called thermal nanoimprint. This is basically hot molding. So we heat the film up, press a stamp of some material into it and mold the material. The challenges in this are actually the temperatures you have to use with the glass are usually near to or exceeding the glass transition temperature. In fact, no, sorry, I beg your pardon. They always exceed the glass transition temperature. They're getting near to or exceeding the melting temperature. One of the problems you have is decomposition of the glass and thermal stress that you build in as a result of processing at those temperatures. So we've had a play with a lot of these different techniques, and we've come down to these 2 as being the most promising methods. There are challenges involved, but you can actually get quite good results with these 2 approaches. Why is it difficult? You know, silica waveguides have been around for 20 years in low loss form. Why is it so hard to do non-linear waveguides? Well, it comes about that a lot of these materials are not very chemically inert, which gives you a lot of problems. Because, for example, they're attacked by the photoresist developer. So the standard lithography process you apply to practically every other material on the planet destroys these glasses. Big problem. Water even destroys some of them, and practically any form of gas plasma will destroy a chalcogenide if you're not careful. So there are some issues there about plasma processing even. So this has driven us into what we would term an unusual phase of wafer-based processing. Some of the best compositions of material for nonlinearity also contain materials that can be difficult to etch. One example of that would be tellurite glass. If you dope it with thallium, you can about multiply the N2 by about a factor of 3. But thallium is really, really hard to etch. Another issue, these materials by their very nature are high index. You make a small, highly confined waveguide, any roughness on the side walls of that waveguide leads to massive scattering. So the lithography and the etching are really quite challenging. And in fact, it turns out that when you do what we're doing at the moment and work with non-reduction lithography, even the quality of the mask can be a challenge when you go around a bend due to the digitization. Because they're high index, they also have high dispersion. And again, this drives you into small waveguides. Turns out there's a magic number beyond which you can't easily get a single mode waveguide that's zero dispersion, and that number is down below the index of chalcogenides and tellurides. So you end up with multi-mode waveguides in the zero dispersion regime. These materials also, by their very nature, have a large coefficient of thermal expansion. So if you're doing high temperature processing on something like a silica substrate, building a lot of thermal stress, cracking, all sorts of things happen. Despite all this, and after 5 years of hard work, we have actually managed to get somewhere, which is why we all feel excited these days. So we spent a lot of time on developing lithography and etching methods for chalcogenides and tellurides, with the following results. So we've got, in arsenic trisulfide waveguides, we've achieved losses of 0.05 dB per centimetre at 1550 with a 7 square micron waveguide. Now when you think that a silica waveguide has an effective area of about 50 to 70 square microns, it is much lower index contrast and has loss that's only marginally better than that. That's pretty good going. When we shrink the mode field even smaller, down to around about 1 to 2 square microns, these losses start going up, and that's an ongoing challenge for us. In telluride materials, we've got to about 4 square microns with basically a loss that's so low out of the water absorption dam that we can't measure it. It's difficult. We've made waveguides up to about 45 centimetres long. You can see on this plot here, this is a cutback measurement of an arsenic trisulfide waveguide. We've got a point up here at 45 centimetres. It's looking pretty good. This is one of these waveguides here with this smaller mode area. We've achieved zero dispersion in waveguide designs and in fabrication. And we've also made nanowire waveguides, which this is an example, that have a gamma of 150,000 per watt per kilometre, which is the largest ever seen for a nanowire glass waveguide. And we've also made buried channel devices such as this one in chalcogenides. Despite all that, there are still a lot of challenges in driving that loss down for those small mode areas, and I'll talk about that a little more in a moment, which drove us to look at some other options, and nano imprint was the one that we went after. This has a lot of advantages. It's fast, it's very low cost, it doesn't use any chemistry at all, which is a great benefit with chalcogenides. The implementation that we've developed, we actually use a soft polydimethyl siloxane stamp. So that's a piece of rubber. It costs very little to make that stamp. It comes off it's moulded off a master that can be reused thousands of times. So if we destroy it by accident, it's no big worry. Whereas a lot of the hard stamp techniques, those stamps cost a lot of money to make. And one very nice feature about it is that you can make complex multi-dimensional devices in a single imprint step. So doing all this, we've come down so far to a loss of 1/4 of a dB per centimetre in a 1.5 square micron device. And importantly, this was actually limited by the film, not by the fabrication method. These here, that's a cross-section of the device. This is a SEM image, and you can see there that the sidewalls on this thing are basically about as smooth as you're ever going to get. There's just no sign of anything happening on the sidewalls, which is why we're getting so excited about this. And we've basically achieved the design for zero dispersion waveguides. The challenge now is to transfer this into arsenic trisulfide, and we'll really start to go places. So having a waveguide has its ups and it has its downs as well. There are some limitations that one has to overcome. So plotted here for an arsenic trisulfide square wire embedded in different materials, so these are the different materials that give different index contrasts, against the size of the device. We've got the effective area of the mode plotted and the dispersion at 1550 nanometers. So you can see it's pretty easy to get down to sort of around about 0.4 square microns, which is quite nice. That's a very small mode. The penalty comes in with the dispersion. First thing you can see is that there's no way to get to zero dispersion until you've got an index contrast of around about 0.9, basically. So that has some quite profound implications in terms of what you can do. It also places some limits on the size range of the waveguide. And this is the zone here where you've got a dispersion less than 50 picoseconds per nanometer kilometre. It's not a very big zone. And in terms of dispersion and control of zero dispersion wavelength, it becomes a bit interesting. What's also important is the single mode limit for these devices is somewhere at about here. So we actually can't get into the single mode regime and have zero dispersion, which has implications as well. We can get pretty close to the minimum effective mode area. The trouble is that puts us over here on these curves, where the slope of this dispersion is quite high, and any error in the fabrication results in moving the zero dispersion wavelength. That is bad news, because plotted here is the four-wave mixing efficiency for pulses in a chalcogenide waveguide that's designed to have nominally a 1550 nanometer zero dispersion. So when you pump it to 1550 nanometers, you get this wonderful response here, 40 dB of gain, right out down to 1300 nanometers. If you shift 10 nanometers either side of that, you see you get quite large changes in that response, which is somewhat challenging to maintain that level of accuracy in a planar process at present. Now, loss also has an impact on everything. This is a plot that Mark Pelusi would dearly love to see us achieve some of the numbers on here. This is the four-wave mixing efficiency versus the length of the waveguide in a particular design of waveguide versus propagation loss and coupling losses into the device. And you can see that basically, at the moment, we're typically sitting somewhere down here, or rather, beg your pardon, here. By going longer, we can gain a little bit, but not a lot. If we can drop off this facet loss, we gain a lot. Propagation loss is a process-driven factor. As you can see, there's some approaches that we've got to try and improve that. How do we get over this huge impact from the facet loss? And this comes about because it limits the amount of power you can get in, and also limits the amount of the generated idler you can get out. So in propagation loss terms, the problem's all about sidewall scattering. And as we go to smaller and smaller waveguides, especially down to like 1 micron wide, the waveguide loss skyrockets. It's all down to the fields in the corners here. Go away, Tien said it's roughly proportional to this, plot that, sure how it is. So surface roughness is critical. How do you reduce it? Big challenge. Reducing coupling losses is an interesting thing that we're working on at the moment. We've taken an approach by making a vertical taper in the height of the waveguide like this, so that we're actually able to bring light in, propagates along, and as it goes through here, it gets to cut off and it's captured in an overlaying polymer waveguide. One challenge with this is that you can increase the electric field inside the material and blow it up if you're working close to the nonlinear limit. You have to adopt flared structures like this. But you go through all this palaver, you can actually achieve really quite high coupling efficiencies into the nonlinear waveguide. There are other impacts from loss as well. These graphs show the evolution of the Raman gain and the four-wave mixing in a device as a function of loss and as a function of length down the device. Probably the most interesting thing to note is what happens to the four-wave mixing. The gain starts out over here and it goes in as the loss kicks into the device as you go down it. So there are issues there in trying to maintain the position of the four-wave mixing gain. Raman gain can be calculated, it shows this sort of behaviour, again, is critically dependent on the loss. Damage, and there's a picture, it tells us 1,000 stories. We don't really fully understand the issues in here. What we've found, though, are two things that help: AR coating the end of the device and actually passivating the surface. And we've now got devices that withstand 600 milliwatts CW in them with square micron mode areas and up to a few gigawatts per square centimetre pulsed. So actual results that we've got out of real-world devices. This shows pulsed four-wave mixing gain in a 6.5 centimetre waveguide. We've got really quite considerable gain here, in excess of 40 dB, and you can even see it's mixing other products in down here. In a sort of system in phase conjugation type experiment here, we put in the CW pump and generate the phase conjugate across the bottom here. We've got wavelength independence right across the C-band. In terms of cross-phase modulation, similar story, we can get full wavelength independence. In terms of supercontinuum, in chalcogenide waveguides, we've got down to about 1100 here. At this end, we don't really know how far we're going. Modelling suggests it's about 2.5 microns. In terms of Raman gain, We've also managed to show that we can get Raman gain here, so we've got a Stokes peak, typically 20 to 30 dB again at the moment. And that is just about it from me.
All right, guys, questions?